Okay, so section 3.4a is based on something called concavity. And concavity is kind of an interesting thing. It's talking about the shape of the graph. So it's really great that at this point in calculus we know how to find max and mins, and we know where the high and the low points are on a graph. But the shape is something else we really want to focus on. Just because you know where the high and the low point is doesn't mean you really understand what kind of shape the graph takes on. So down below here we have three graphs that we're going to draw. This is graph 1, graph 2, and graph 3. And we're going to talk about the types of concavity, because there's different types of shapes on a graph. So type number 1, this first graph over here, is going to be a graph that I'm going to connect from A to B, and I'm going to kind of make this graph up something, I don't know, something like this, where A and B are the endpoints of the graph. And we're going to call this f of x. Well, this type of graph is a graph that we call concave up. So I'm going to write under here, concave up. It's facing upwards. The idea is it's cupping upwards. If it was to be raining into this graph, all the water would puddle up into the cup. Now, that's kind of a cheesy analogy, but that's the idea, is that it's faced upwards like a cup. And so concave up, a lot of times I just say CU for concave up, is describing that shape. The fact that it's facing in this upwards, I'm kind of highlighting it here, but this upwards direction. So that's type 1. Now graph number 2 here is going to be the total opposite of that. It's what we call a concave down graph. It would be something more like this, where A and B are the endpoints. But now if you look at it, if this is our function f of x, it's shaping the complete opposite direction. If it was to rain on top of this graph, all the water would slide off the edges, and the cup is facing downwards. So we call this a concave down graph. And I'm going to write that down here, concave down. Or my shorthand is going to be CD to keep it simple. So we have concave up, we have concave down, and then we have this third type of graph that really kind of falls in the middle of all this. It's really no concavity. And the only type of graph I can really think of for this would be a straight line. If from A to B it's a total straight line, well, then we don't really have like a concave up or down graph. It's not shaped up or down. So we say no concavity for this graph. There is no concavity. And so we kind of really only have these three situations. And what's interesting is a function f of x can kind of take on multiple concavities. You can have more than one shape in one graph. So my next note here says a single function can exhibit both types of concavity. And I'll show you what I mean. I'm going to make up a graph here. Something that maybe goes like, I don't know, let's make it interesting. This. This is my graph of f of x. I'll draw a little arrow on both ends. And the reason I'm saying this graph is so interesting is because it has multiple concavities. If you notice, the beginning of the graph here is very much concave down. It's all shaping in the downwards direction. So it's definitely concave down. I'll just write CD. But eventually it's going to make a change here. It goes from concave down to, concave up. It's facing in the upwards direction. If it was to rain, it would make a big puddle inside of that part of the graph. So this concave up portion, which is right here, transitions somewhere from the down to the up. Somewhere in this area, in this red section, there's a change. And so I'm going to guess that that change happens somewhere around here. That point is where the graph switches from down to up. Then the graph hits a little bit of a kink up here. But after the kink, it's still facing in an upwards direction, so it's still concave up. And then eventually it makes a transition back to facing what I would say is concave down again. So this looks back to concave down, and that transition point is probably somewhere around here. What we're going to learn today is how do we test for concavity? How do we find the shape of a graph if I can't actually see the graph in front of me? This is nice. I can just visually look at this graph, identify the concave up, concave down, but I want to get more specific. I want to know these points of transition. Where exactly, precisely are they on the graph? So where are these points? And what if I can't see the graph? How do I find the concavity? So my next note here that we're going to write down is suppose you have a function and you want to know if it's concave up or concave down. How can we figure it out? So we're going to talk about there's a test you can run, a test of concavity, and there's two things, I'm going to say A and B here, that we look for. So part A is this. The function f of x is going to be concave up. So I'm going to write f of x is concave up if we discover f double prime of x, the second derivative of the function, is a positive number, is something greater than 0, something positive. If the second derivative is something positive, the original function shapes upwards, which is kind of an interesting thing. So note, the second note here, part B, is going to be the opposite of this. If a function, f of x, is concave down, then we know that the second derivative, f double prime of x, is a negative number. It's something less than 0. So the sign of the second derivative tells us the shape of the original graph, whether it's facing concave up or concave down. And we're going to use that to run some tests. So we're going to try some of these and kind of take a look at it. So here's an example. Let's try one. It says determine the intervals of concavity for the function f of x equals x to the fourth minus 4x cubed. Now the idea here is if you could graph this on your calculator, you probably could just eyeball the concave up, concave down answer. But we want to be able to do it in a non-graphing calculator section. We want to be able to figure out the concave up, concave down of this graph without actually seeing it. So here are our steps. Step 1. We're skipping over the process of finding max and mins, and we're going to concavity, which means we're going to need the second derivative. So we're going to want to find f prime of x, but then off of that, we're going to want to find f double prime of x. So I'm going to power rule this thing twice in a row. X to the fourth minus 4x cubed. That's going to be 4x to the third minus 4 times 3 is 12x squared. Alright, and then I'm going to power rule that again. So 4 times 3 is 12x squared minus 12 times 2 is 24x. There's my second derivative. And we're going to be figuring out when is it positive and when is it negative. So just like when you're doing max and min problems or you're making a sign chart, we're going to set this thing equal to 0 and we're going to solve for x. And I think I'll factor out a 12x to make this easier. Divide 12x out of the problem, you just have x minus 2. So now we have either x is going to equal 0 because 12x equals 0, or we're going to have x is going to equal 2. And these two spots are going to go on a sign chart. We're going to test them to figure out what's going on with the second derivative. The other thing we should probably ask is, does it ever turn out to be a D and E situation? Does f double prime ever equal D and E? And here's our f double prime. I'm going to say no on this one. We don't have any fractions or any weird stuff. I don't think anything would make this D and E. So, not a situation here. We just have 0 and 2 down at the bottom here that are going to be our points to kind of focus on. So let's go to step number 2. Now that we got this figured out, step 2 is we make a sign chart, just like we do with max and mins. So step 2, let's sign chart this thing. Now, the sign chart's going to be interesting because instead of doing max and mins, we're working with the second derivative. So on the top of the sign chart, instead of finding the sign f prime, we're going to find the sign of f double prime of x. And we're still using it to discover the behavior of the original function. So I'm still going to write on the bottom of my chart behavior of f of x. That's still what we're trying to find. So we're going to find the sign of f double prime to get the behavior of f of x. And remember, if you don't put these labels over here on the side of your chart, the AP graders aren't going to give you any points because your number line chart's going to mean very little to them unless it's labeled. So with no labels, you really get nothing for the points. So you got to be really careful to make sure you're getting in that habit. So we've got 0 and 2 on the chart here. Now what we're going to do is we're going to pick numbers in between 0 and 2, like 1, or after 2 we could use 3. Before 0 we could use like -1. And you can pick any numbers you want as long as it's before 0 and after 2. Like, you don't have to use 3, you could use 5 or 6 or 7. And we're going to take those numbers and we're going to find the sign of f double prime. So we're going to find what is f double prime of -1. What is f double prime of 1? And what is f double prime of 3? And every single one of these, we'll plug it in and we'll get an answer. Now remember what f double prime was on the last page here. It was 12x squared minus 24x. So we're plugging it back into this. So we're going to do 12x squared, so 12 times negative 1 squared minus 24x it was. So we're going to do minus 24 times negative 1. And then we're going to do 12 times positive 1 squared minus 24 times positive 1. And we're going to do 12 times 3 squared minus 24 times 3. And to be completely honest, we don't really care about the answer so much as we just do about whether the answer turns out to be a positive or a negative answer. That's really all we care about. So you can do a lot of this math in your head. I realize this first one's going to be a positive answer. And when you plug in 12 minus 24, that's a negative answer. And then 3 squared is 9 times 12. That's a really big number. This is going to be another positive answer. So, I mean, the fact that the answer has a specific number doesn't really matter. I just care about the sign. And I got positive, negative, positive. So that means at negative 1 up here, we got a positive answer. At 1, we got a negative answer. And at 3, we got another positive answer. And that's going to tell us about the behavior of this graph. We now know that it goes positive, negative, positive. And what that means is this. It means that the graph is shaped concave up because it's positive, and then concave down because it's negative, and then concave up because it's positive. And so now we know that the shape of the graph is up, down, and up, and these points at 0 and 2 are the points where they make the transition and they change from up to down. So now we know the shape of our graph. Concave up, concave down, concave up. And I want to put a little note back here. The points where f of x change concavity, so the points where f of x are changing concavity are called points of inflection. Points of inflection. And points of inflection would be from the number line. So going back to that number line real fast, I'm going to erase down below just so I have some space down here and try and fit this in. But these points right here at 0 and at 2 where the concavity change are called points of inflection. Points of inflection. Those are the points where concavity changed on the graph. Okay, so now that you're kind of getting a handle on how to make a second derivative sign chart and test for concavity, going back to that note that we made here, I wrote the point where f of x changes concavity are called points of inflection. And I have 3 little graphs down below here because I want to draw 3 potential pictures of different types of points of inflection. So on the first graph down here, I'm going to draw a function that looks something like this. Call this f of x. And I just want to make a note that this is a graph that switches from concave up to concave down. And right about here, we're going to say that's at A. A is a point of inflection. Switches from up to down. So A would be a perfect example of a point of inflection. Another graph we could draw, maybe something more like this. Well, I don't know if I like that. Let's make it a little less like this. This is another graph where a point of inflection happens somewhere around here. It's switching from concave up to concave down. It's a little steeper, but I'm going to say A is right about there. And then I'm going to make a third graph that's going to be a little more unique. It's going to look something like this. It's going to have a kink. And this is a graph where it goes concave down, then it hits a kink, but then it's concave down some more. And so we would say A here is not a point of inflection. This is not a point of inflection at A. A little bit different. So point of inflection at A, not here, not a point of inflection. You could write a little note in your notes because the concavity does not change. So I have another example here for you, and you could pause the video and kind of give it a try a little bit here. But it says find all points of inflection for f of x equals x to the 4th power. So for f of x equals x to the 4th power. And we're going to try this one. We're going to go through our steps. So step 1 is we need 2 derivatives up. We got to go to the second derivative. So step 1, let's find f prime of x with the power rule. X to the 4th will be 4x cubed. Then we're going to find f double prime of x, power ruling it again, so 4 times 3 is 12x squared. Then we're going to set it all equal to 0, and we're going to solve 12x squared equals 0 by dividing by 12. Dividing by 12, so 0 equals x squared, which means 0 equals x is our answer. And we're going to say, is this ever D and E? We got to think about that, because it could be, does this thing ever get you a D and E situation? And it's not in a fraction, there's nothing weird, so I would say no to D and E, not a concern. Now, here's a little bit of a catch. At this point, this answer, x equals 0, is not necessarily a point of inflection. It's called a possible point of inflection. Possible point of inflection. And this is actually really important to write down, because on an AP test, a really common error by students is to solve for the second derivative, set it equal to 0, and get an answer like this, and then say, oh, it's a point of inflection because the second derivative equals 0. And the truth is, it's only a possible point of inflection. It's not guaranteed until you make a number line and prove it. So you want to be super, super careful about that. So possible point of inflection. Okay, so let's go on to step 2. Step 2, which I'm going to write over here, step number 2, is we're going to make a sign chart. And we only have one number to put on our sign chart. That's 0, x equals 0. And we're going to label it, because if we don't label it, we get no points. So sign of our second derivative, f double prime of x. And it's going to discover the behavior of f of x for us. And what we're going to do is we're going to pick a number before 0 and after 0 to test. Any number we want, like we could do 5. Or how about we do 1, because 1's always easier. We could do like -1. Those are easy numbers. And we're going to find the sign of f double prime. So we're going to plug these numbers in to f double prime. So f double prime of -1 and f double prime of +1. And the answer doesn't really matter to us. It's just whether it's positive or negative. So what was f double prime? It was 12x squared. Oh, this is easy. We can do this one in our head. 12x squared is going to be 12 times -1 squared. And -1 squared is a positive 12. And we're going to do 12 times 1 squared. 1 times 1 is 1, times 12 is 12. This is a unique case. We got a positive number, and we got another positive number. Which means on my number line, at -1 we got positive values, and at +1 we got positive values. All positive numbers for this answer. So, what does that mean for us? Well, that means the graph is concave up and concave up some more. Which means 0 here is not a point of inflection like you would have assumed. It's actually just a point on the graph. There's nothing unique to write down about 0. It's just not a point of inflection. What we know is the graph is concave up and concave up some more. Now, we could go draw a graph. Remember, we're kind of figuring out the behavior for f of x, and f of x was equal to the original problem, x to the 4th power. Well, we have the luxury of we're taking notes right now, so we could check this on a calculator and graph x to the 4th power and see what it looks like. And if we were to graph it, we're going to notice what's going on with it. So draw a little graph. Oops, I'm getting ahead of myself here. Sketch yourself a little graph of this thing. I guess I'll put it down in the corner. Here's my graph. F of x equals x to the 4th power is basically a parabola. Here's f of x equals x to the 4th power. It's a graph that goes from concave up to more concave up. Here's 0. Here happens to be a place where both f prime and f double prime equals 0. That's why it's on our number line up here. But the graph goes concave up to concave up, and it never changes concavity. So kind of a trick question here. So the next slide that I accidentally flipped to is a warning slide. I would put this in your notes. Serious warning here. Not every point, I call them C, where f double prime of C equals 0 or f double prime of C equals D and E is a point of inflection. We just learned this, that not every point, just because the second derivative equals 0, makes it a point of inflection. So it's not safe to make that assumption. So you need to be very, very careful about that. A lot of people make those assumptions, and they're actually wrong.